I want to talk a little more about GCDs and LCMs in this section. First theorem we'll talk about is this. Suppose a and b are integers not both 0, then I claim that every common divisor of a and b is a divisor of the greatest common divisor. Now there's two proofs we'll give here. One proof doesn't involve the fundamental theorem of arithmetic, and then later we'll give one that makes use of the fundamental theorem of arithmetic. So I want to show that every common divisor is a divisor of the greatest common divisor. Okay, so let's let D be the greatest common divisor, and take a look at some other common divisor. So let's let E be any common divisor of A and B. Okay, by the GCD LC theorem, we know D is AX plus BY for some integers X and Y. Okay, now E is a divisor of A, so since E divides A and E divides B, we know that E is a divisor of any linear combination. So E divides AX plus BY. Okay, that was one of the early divisibility properties we proved. But AX plus BY is the GCD. E divides D. Okay, so there's a proof that just uses the GCD LC property. There's another proof very similar to this for the following theorem. If A, B, and C are integers such that A and B are both divisors of C, and A and B are relatively prime, then the product, A times B, is a divisor of C. This is a theorem that would certainly be false if A and B are not relatively prime. And the proof is similar in nature. You're going to use GCD LC. I think I'll let you do this for a homework problem, similar to the last proof we just did. Okay, the least common multiple. The least common multiple of two non-zero integers, we'll denote with square brackets, square bracket AB, is the smallest positive integer that is a multiple of both A and B. So again, it's a self-defining word. And certainly the least common multiple exists, since, for instance, A times B is a common multiple, and so by well-ordering property of the natural numbers, there's going to be some smallest number that is a common multiple. Okay, theorem. Suppose A and B are non-zero integers, then I claim the product of the LCM and the GCD is just the product of the two integers. And of course, if A or B was negative, we need to put absolute values here, because LCMs and GCDs are always positive quantities. And part 2, every common multiple of A and B is a multiple of the least common multiple. So in particular, if A and B are relatively prime, then from the formula in part 1, the least common multiple is just the product of A and B in absolute value. So there are two proofs of this theorem we'll see. Again, let's do a proof that doesn't use the fundamental theorem of arithmetic. So in this proof, we just let capital R be the quotient A times B divided by the greatest common divisor of A and B, which is certainly an integer because the greatest common divisor is a divisor of A, say. And our goal is to prove that R is in fact the least common multiple. So let's go ahead and just assume A and B are both positive here. So note we can write R two ways. I can write it as A over the GCD times B, or as B over the GCD times A. And so we can see that capital R is a common multiple of both A and B. Okay, so suppose now that M is any common multiple of A and B. Say M is A times S, and M is B times T for some integers S and T. And our goal is to do what? We want to show that M is in fact a multiple of capital R. So let's start with the GCD-LC theorem that says the greatest common divisor is AX plus BY for some X and Y and Z. Multiply both sides by M. So M times the GCD is MAX plus MBY. Substitute in that M is BT in the first term, and substitute in that M is AS in the second term. And then we have a factor of AB common to both of these. And then finally just divide both sides by the GCD. So recall R is AB over this. So when you divide by that, you're getting the factor of R sitting right here. And so we get a multiple of R. Okay, now this proof is a little mysterious. We're going to give a much more what I call intuitive proof of this property by using prime power factorizations. Okay, so let's first of all come up with some formulas for GCDs and LCMs in terms of the prime powers. So suppose A and B have factorizations of this type. And note, this is a very useful trick in number theory to say two numbers always have the same set of prime factors. Well, of course, that's not true for arbitrary A and B. But by allowing zeros in the exponent positions, I can use exactly the same set of prime factors. And so that makes proofs much more elegant or much cleaner in nature by allowing these zeros in the exponent positions. So here's the property. The greatest common divisor, you take each prime and you raise it to the minimum of the exponents dividing A and B. And then just take this product. And for the least common multiple, in the exponent position, you're going to take the maximum of the exponents. And it makes sense. To be a divisor of A and B means the power of P that's going to appear as a common divisor has to be smaller than the power of P occurring in both A and B. And so you want to take the minimum. Whereas to be a multiple, the power of P occurring in a common multiple has to be at least as big as the power of P occurring in each of A and B. So to give a formal proof, we need the following lemma. So suppose that P is a prime, that A and D are integers, with D a divisor of A. If P to the E exactly divides D, and P to the F exactly divides A, then we claim that E must be less than or equal to F. Okay, so why is this? Well, P to the E exactly divides D, so we have P to the E divides D, and D divides A. Put those together by the transitive property, P to the E is a divisor of A. Well, that means that E must be less than or equal to the biggest power of P dividing E. So immediately we get that E has to be less than or equal to F. And that's all there is to that lemma. But that's the key lemma to really giving a formal proof of this theorem. Let's just take a look at one of those two properties, the GCD property. So I'll call this right-hand side quantity D, say. And, okay, so let's first show that D is a common divisor of A and B. So plainly, D is a divisor of A since each of these prime powers is smaller than EI. Right? So A, let's write down what A is. A is the product of PI's to the EI's, and B is product of the PI's to the FI's. So since each prime power is smaller than the EI, clearly D is a divisor of A, and likewise D divides B, since each of those prime powers is less than or equal to Fi. Okay, so D is a common divisor of A and B. Okay, now let's suppose that E is any common divisor of A and B. And give E a factorization. So again, I can use exactly the same set of primes. Pi to the GI, allowing zeros if necessary, for some GI greater than or equal to 0. Okay, well, E is a divisor of A means what? By the lemma we just looked at, we have Pi to the GI is the power of Pi dividing E, and therefore GI must be less than or equal to the power of P dividing A, which is EI. Our lemma. And E divides B implies that GI is at most Fi by the same lemma. Therefore, GI is less than or equal to both EI and Fi, so GI is at most the minimum of EI and Fi. And once we have that, all of these are smaller than the minimums, therefore E is a divisor of D. QED. So we were trying to prove that D was the greatest common divisor. Not only did we prove that D is the greatest common divisor, we've also proven that every common divisor is a divisor of D. So we have given another proof of this theorem we started with. Okay, now let's return to this other theorem we gave a proof earlier of. For any two positive integers a and b, The product of the GCD and LCM is the product of the two numbers. So we gave a rather mysterious proof to start, but now let's give a very straightforward one. So just using prime powers. Okay, so let A be product pi to the ei, B product pi to the fi, with our usual trick allowing 0 exponents. If necessary. Then AB times square bracket AB is what? Well, the GCD, we take the minimum of the exponents, and for the LCM, we take the maximum of the exponents. Aha! Grouping those terms together, we just add the two exponents, so we'd have pi raised to the minimum plus the maximum. Now, think a minute. What do you get if you add the minimum of two numbers to the maximum of two numbers? Well, one of the numbers is the minimum, and the other is a maximum, or they both could be equal. So we just get the sum of the two numbers. Pi to the ei plus fi, which equals what? Well, that breaks up as the product over the pi to the ei's times the product over the pi to the fi's. That is exactly A times B.